relativistic electrons, so the cosmic rays. And emerging galaxy cluster, this can come from very different sources. We have radio relics that are these very elongated megaparsec size structures, which are located usually in the cluster outskirts. And the basic idea here is that they are tracing, they trace the shock propagation outward. And since during the shock propagation, the ICM is compressed, and so also the magnetic field is compressed, what we have is that the emission is highly polarized. On the other hand, we also have radio halos, which are always megaparsec structure, but they usually follow the intracluster medium that we found from the X-ray observation. And the idea here is that they trace the merging turbulence caused by the merger. And for this reason, since the turbulence is a random event, we found that this emission is unpolarized. Last but not least, synchrotron emission from this ultrarelativistic and magnetic field interaction also comes from the supermassive black hole in the form of radio galaxies. However, in a galaxy cluster, such radio emission is very different from the radio galaxy that we found in the field, which are characterized by a very symmetric double-lobed shape. Indeed, in galaxy clusters that are both merging and relaxed cluster, such radio galaxies present a very fun shape in the form of tails, which suggests that there is a sort of interaction between the motion of the galaxy and the cluster weather. And I should also mention that relics and halos, which are diffuse red emission, which is not connected to any optical counterparts, is usually characterized by very steep and sometimes curved spectra, meaning that they are both old structure, but also that they are very well detected at low radio frequencies, while they can become faint or undetected at higher frequency. And in this talk, I will mainly focus on radio relics, although I will also speak about a little bit of radio galaxies and their importance in emerging cluster. So, as I said before, radio relics are supposed to trace the shock propagation outwards. And the main formation scenario for this structure is that is the so-called diffusive shock acceleration mechanism. And according to this model, basically the particles from thermal pool crosses several times the shock fronts, and every time they gain energy till they acquire the ultrarelativistic energy to emit via synchrotron radiation. And this is actually also the model that explains, for instance, the supernova remnants, but unlike the supernova remnants, the cluster shock are characterized by very low Mach number, meaning that we are talking about Mach number about 2 or 3. And so for this reason, this mechanism is not always efficient enough to justify the presence of such long structure and very bright radio structure. Another mechanism that sometimes is invoked to explain radio relics is the so-called reacceleration mechanism, where basically it involves the presence of a fossil cloud which is swept up by the shock that is able to reaccelerate particles because this fossil plasma is already accelerated in a previous stage. And usually this cloud of fossil plasma is seen in the form of the lobes of radio galaxies. So this mechanism is actually more efficient, but it requires the morphological connection between the tail and the radio of the galaxy and the radio relic, which is not always the case. So I should also mention that a very nice thing about the diffusive shock acceleration scenario is that there is a very nice connection between the spectral index that we measure at the shock and the Mach number of the shock, meaning that if we obtain the radio Mach number, we can compare that with the one that we obtain from the X-ray detection, and if these two measurements are matching, we have a good test for the DSA. So among the very large number of still open questions that we have for radio relics, today I will mainly focus on these 3 bullets. Namely, if we really understand the spectral index gradient across the radio relic, which is also connected to the understanding of the aging of particles in the back of the shock, what are the properties of the relic shock, and how do they interact with the radio tails? And in order to try to answer to the first question, I've been studying the merging galaxy cluster CISA J2242, which is better known as the Sausage cluster. This merging cluster is characterized by the presence of a very nice double radial helix, located one in the north and one in the south, and also by a central diffuse radio emission, which is associated with the radio halo. And the thing that makes this cluster particularly suitable for the study of spectral index gradient is the presence of a very nice radio relic in the north, which is very long and is very narrow, and is also characterized by a very low inclination angle. And is actually this radio relic is also the reason why we give this nickname to this cluster, because to its peculiar shape. The things that we noticed while we were studying this cluster is that this is not a continuous structure, but is formed by several filaments. This is actually not really a surprise, because we see from simulation that is here in this movie that radio relics are complicated structure, and most importantly, it's very unlikely that the distribution of magnetic field and electrons remains constant along all the relic length, that in this case reaches the 2 megaparsec sizes. And yes, so for this reason, since this this relic is characterized by filamentary shape, we only focus our study for one single filament. Oops. And what we found here is something that we really expected, at least qualitatively, from the aging of particles, because we see a flat spectral index at the shock location, which basically is suggesting that the shock is accelerating particles, while in the downstream region, so in the back of the shock, we see a steepening, meaning that the particles are losing energy, very likely due to inverse Compton and synchrotron radiation. The other thing that is pretty nice from this work is that if we obtain the Mach number from the spectral index at the shock, we found that this radio Mach number agrees very well with the X-ray detection. So a sort of confirming on the diffusive shock acceleration scenario. And in order to try to explain more quantitatively this trend of the spectral index, we built a model which basically takes into account a single shock Mach number, magnetic field variation in the downstream region, downstream aging of particles, and also we took into account the geometry of the merger. And what we found is that while for the surface brightness profiles obtained at the 4 radio frequency that we use to build the spectral index gradient is quite well done, for the spectral index gradient itself, we don't find a very nice match, especially if you look at the very downstream region. And one possible explanation to this not matching between the model and the observational data could be again related to the filamentary shape of the nature of this relic, because maybe the assumption of a single Mach number shock and single magnetic field at this shock position is still too simplistic to explain this filamentary shaped relic. So I should also mention that from this model, although it's not very well representing of our data, it seems to suggest that the Mach number is higher than the one that we found from the X-ray and also from the radio spectral index map. But I should also mention that at least for this particular case, the fact that we see discrepancy between the X-ray Mach number and the radio Mach number is not really surprising, because the relic is located in a position where it was not possible to use high-resolution Chandra imaging, but we could only detect the shock via Suzaku observation, which is very sensible, but is also very poor in terms of spatial resolution. So in the end, we basically didn't resolve the shock. So in order to really analyze the properties of relic shock, we need to have high-resolution Chandra observation. And in order to try to analyze that, I've been studying this other cluster, the Zwicky cluster 0008, which again presents a very nice double radio relic, although in this case we found that the eastern relic is much larger than the eastern one, is about a factor of 5 larger than the western relic. Also, for the studies done so far, we're not able to detect any kind of diffuse radio emission in the center, and it is puzzling for the theory that try to explain the formation of radio halos. And from the X-ray point of view, this cluster presents a very disturbed morphology with the presence of a cometary shape that is identified as a ballet, very similar to the most famous ballet cluster, and also by the presence of two discontinuities that are located in the very proximity of the two radio relics. And for this reason, to analyze these two discontinuities, we extracted the surface brightness profile in two sectors that cover the two X-ray discontinuity. And what we found is that while for the eastern relic we confirmed the presence of a discontinuity that is well described by a Mach number of about 1.6, for the eastern relic, we just found a sort of change of slope in the surface brightness in a position that is actually not coincident with the radio relic. I should also mention that at the location of the radio relic, we don't find any indication of shock, and this is quite puzzling, although the position of this radio relic is quite unfortunate because it's located in the very edge of the CCD, meaning that maybe we are not observe any discontinuity, not because there is no discontinuity, but because we are losing X-ray photons because of instrumental limitation. So we compared this X-ray analysis also with the previous spectral index map made between 610 MHz and 1.4 GHz. And again, what we found is that for the western relic, the Mach number obtained by the spectral index map is quite in agreement with one from the X-ray, at least if we consider the error bars. While for the eastern relic, we found that the radio analysis suggests the presence of quite, well, not strong, but a shock Mach number of about 2. We also confirmed actually the nature of this discontinuity by looking at the temperature profile. And again, for the western relic, we confirmed the presence of a shock because the temperature is decreasing across the discontinuity. While for the eastern relic, we actually, the two measurements made in the back and ahead the discontinuity agrees to each other. So it's not, we cannot really say much more. And actually, if we exclude the eastern relic as the big puzzle of this cluster, we actually have another puzzle that comes from the western relic, because as you can see from the image, the radio relic does not trace entirely the X-ray discontinuity, which is quite puzzling, but the possible explanation is actually coming if we consider also the third question of this talk. Before doing that, just let me explain what we expect from the radio tails and radio relic interaction. And to do so, I will just briefly show this picture, which is a work done here by Reinhardt and Philippe about the merging galaxy cluster Able 3411, 3412, which shows a very nice cometary shape X-ray image of the cluster and also a radio relic here. But the interesting part of this cluster comes from this region here in this box, because here at the location of this diffuse radio emission, they found confirmed X-ray discontinuity. But the thing that is pretty interesting comes from the spectral index analysis of this region. Because at the AGN position, we see that the spectral index is flat, meaning that the particles are very recently ejected, so they are ultra-relativistic, they are young. The spectral index steepens on the radio tail, meaning that particles are becoming old and they are losing energy. But what we found that is interesting is the presence of reflecting of the spectral index at the location where the X-ray discontinuity is positioned. And this is again seen as a sort of interaction between the shock wave that is reaccelerating particles at this position. And as I said before, this can actually be the case also for the Zwicky cluster that have been studied this year, because if we zoom on the western part of the cluster, we see that in the proximity of the western relic, there are 3 radio galaxies that, and also most importantly, that there is hints of emission in the region in between this relic and the radio galaxy. And such a faint emission is actually very well seen if we decrease the resolution of the image, because this is actually a trick that we usually do for highlights the presence of faint and diffuse emission. So the big question here is that if these 3 radio galaxies can be actually the source for fossil plasma to justify the presence of this radio relic, and could actually explain the reason why the relic does not trace entirely the X-ray discontinuity, because simply at these 2 positions we don't have fossil plasma to reaccelerate. However, with this data in hand, we cannot say much more than this. We are waiting for the analysis of LOFAR data, and why LOFAR is very simple, because it's a new radio telescope array that is working at 150 MHz, so at low frequency, and is also characterized by an incredible sensitivity. And we also have a very nice case where from the JVLA was not detecting anything from the JVLA observation, but switching at LOFAR observation, actually a very faint and spectral emission have been detected. So we are waiting for analyze this data and maybe have a better detection of the emission in this part of the cluster. Actually, another very nice tail relic connection also comes from the Sausage cluster, but in this case we have to switch to the southern relic. And if you look at the zoom on this part of the cluster, we see that this relic is complex, is quite a mess, and is not characterized by a filamentary structure, but is formed by several arms of diffuse emission. And the thing that's pretty nice that we notice is that there is actually also here a radio galaxy very close to the southern relic. And for the first time, we were able to actually detect a radio jet that is connecting the spectroscopically confirmed AGN with the diffuse lobe of the radio galaxy. So we went to and we start to analyze the spectral index of this tail, following the quite peculiar shape of this relic, also avoiding point sources that could affect the spectral index analysis. And what we found here is that at the AGN location we have a quite flat spectral index. We see steepening in the region in between that covers the jet and the lobe. And we also see a reflecting of the spectral index in a region that we call the reacceleration region, that is basically this part here. So we try to model this spectral index behavior by looking at by assuming a fossil electron cloud, which basically describes well the behavior of a radio galaxy. So basically we assume a power law emission plus an exponential cutoff that takes into account the spectral index aging. And what we also assume a Mach number of the shock of 2.4, which is basically a number that is coming from this detection of the spectral index measured at the shock. And what we found is that indeed the model seems to describe quite well our data. I should also mention that also for this cluster we have a detection of a shock from Suzaku, and again also here the Mach number is not really matching our proposed radio Mach number, but again since this detection is made with Suzaku, it could suffer of instrumental limitation. So I hope to have just a few minutes to talk about. This is actually a work in progress. I don't really have a lot of results from this part, but it's basically a work that I will do in the next month, in the next year. and basically is the study of magnetic field variation across radio relic. And why this is important, as I said before, because magnetic field variation could actually help to try to explain the spectral index analysis of radio relic. When we study magnetic field, which is actually something that is very complicated because magnetic field in galaxy cluster are very low intensity, it comes basically from the by studying the polarization of the relic itself. Because what it happens that when the shock is propagating, the shock compress the magnetic field, which is basically aligned with the shape of the radio relic. And here basically is plotted the electric vectors which are perpendicular to the polarized to the magnetic field vectors. One complication that also comes from the magnetic field estimation is the fact that despite the relics are located in outskirts of the cluster, they are still embedded in the ICM, which is magnetized. And for this reason, the polarized emission can suffer of a variation of the rotation angle. So basically what we detect is the polarized emission with a polarization angle that is not the real one. And such rotation basically depends on the frequency or the wavelength at which we observe, and also it depends also to the phi parameter, which itself depends on the distribution of electrons and on the magnetic field. And basically now what we have that is pretty nice is that these JVLA observations are wideband observations. So with just one single observation, we can actually have more than in principle, more than 1,000 channels that gives the estimation of this rotation angle. And the very preliminary result of this work that I'm doing that actually use only half of the wideband and is done at quite low resolution, is showing that this phi parameter, so this parameter here, is varying across the radio relic, which can be seen as a variation of magnetic field, of course, if we assume that the distribution of electrons at the relic location remains constant. And again, as I said before, this is a work in progress, so stay tuned because it's going to be something really interesting. So this is just a summary of my talk. And just to summarize, I've basically shown that the sausage relic, but actually this is not only the case where we see that our high resolution observations are showing that the radio relics are composed by filamentary shape. And actually we were not really able to model the spectral index gradient across this relic. We found two other very good hints of tail-relic interaction, which is actually helping people by observational point of view to explain relic formation scenario by means of reacceleration mechanism. I would also to stress that we really need to have high resolution X-ray observation to really detect the sharpness of the X-ray discontinuity. And last but not least, the big open question is how the magnetic field are interacting with this filamentary structure of the radio relic. So, thank you.
Sausage is so nice, it's still in pieces. So I have two questions. One, is there anything characteristic about the sizes of the pieces?
Well, in this case, we see that, do you mean in length or? Yeah, that actually depends on the distribution of magnetic field and the electrons, because which are we seeing is basically that. So the length basically could be, for instance, the length of a previous fossil cloud that is located there. We don't have any kind of suggestion of a presence of radio galaxy at this location, so we cannot really say much more about the length of the relics. Although, again, the magnetic field variation studying maybe could help in this sense.
Anybody else has? So on the eastern end here, in one of
This
the
one.
pictures you showed, it almost looked like the one that was going to the north was connecting.
Oh, wait, let me go back.
Yeah.
Do you mean
So,
this one?
so it
Here.
almost looked like.
Yeah, this is actually another thing that is pretty interesting, because if you look at, for instance, this tail here, you would expect that from this image that AGN is here. Actually, the AGN is, if you look at both the optical and the high resolution image, you see that the AGN is here. So it seems that here there is another filament that breaks the AGN, and here there is actually this other new relic emission that if you keep going here, it seems that breaks the tail, which is again another actually suggestion that radio galaxy affect the presence of radio relic, but on the other hand, also the shock is affecting the galaxy population. And we have several of these examples because, for instance, let me see if I have a nice picture of that. Yeah, maybe here. Here, this one, for instance, is another very nice indication of radio tail, which presents this strange diffuse emission here, this bottleneck morphology, which seems that there is a sort of interaction between the shock and this tail. And the thing that actually is pretty nice because there are now new models that are developing, which are trying to study the interaction between the tails and shocks. And it seems that these models, this simulation, represent very well this kind of bottleneck morphology. So there is still. But yeah, this relic here is actually also very puzzling because, as you can see from this image, from Chandra image, is very far from the X-ray emission. Again, here there is the work by Hoang et al. In 2017 that they tried to use, again, Suzaku to obtain a shock measurement. They found it, which seems to be in agreement with the spectral index at this location. But again, it's very far from the cluster, so it's still not clear if can be traced.
So in the piece that's the most to the
This one?
east, is there a galaxy in there?
No.
Just
No.
diffuse emission?
Yes.
All polarized?
No, at least from the what we see from the optical image, there seems not to be anything. There is actually one of these 2 points here is a distant quasar, so it's not associated with the cluster. But it seems to that there is no any, at least for now, no radio galaxy present in the proximity.
Okay. Just a question: when you got somewhat different Mach numbers depending on whether you measure things from the relic or
Yes.
from the X-ray, can you get any third kinds of motion Mach numbers from any of those tailed radio galaxies? Do any of them have, X-ray tailed halos a little bit around them that you could measure those?
In principle, I think yes. Yeah, the problem with the estimation of of Mach number from the spectral index is really related to the projection effect, because if you as in this case where the merger axis is very close on the plane of the sky, you have a very nice estimation of the front. Although we see that is not really the case because also very small projection effect seems to give a misleading Mach number. So if you have the projection effects that are bigger, you can mix population from different, you can measure the electrons coming from different populations. You mix different ages, so you have a Mach number that is not really the interpretation of the shock, but only because projection effects. So in this case, actually, this is the reason why this cluster here is very nice, because we see that the tail is perpendicular to the shock, and it seems that everything seems to match very perfectly.
Can you explain again the discrepancy between Mach numbers? I thought one analysis showed that the radio index grid was, and then
This one, or
yeah, on the previous, here. This analysis shows that the radio Mach number and X-ray agree
yes,
to each other, and then you do different analysis on these.
Yes, actually, yeah, exactly. Basically, this idea is basically that we have this spectral index map. We measure the spectral index in a sector that is coincident with the front, assuming, of course, that we have no projection effect. What we saw actually is that even at this position, we see curvature in the spectral index, meaning that it is not really the shock front, because at the front, if the particles are just like recently accelerated, we should have exactly a power law. So we try to model this, including also geometry, and assuming a single Mach number that could be a completely wrong assumption, we see that the best fit, which basically comes from the fit of the four fluxes, we see that it seems that is pointing to a higher Mach number, but this number could be completely wrong as well, because it doesn't take into account possible variation. But yeah, the point here is that even if we have a very nice match between the two Mach number, is actually a wrong, is a fortunate case. We were just fortunate.
Thank you, Gabriella. Our next speaker is Dr. Virial Ntampaka. Virial is currently a data science initiative fellow at the ITC, and her research focuses on machine learning and using those methods to tease out complicated patterns in the data that are accessible through traditional methods. And Virial got her PhD from University last year, and her PhD supervisor is Materie, and he was a ITC fellow here a few years ago. And before Virial went to graduate school, and she has been a middle school and high school teacher for 10 years. So if you use a cell phone during her talk, she'll confiscate you. Okay, so today Virial is going to talk about the dynamic mass measurement of galaxy clusters using support distribution definition.
Great. Thank you very much. Can everybody hear me? All right, great. So as a former middle school teacher, there's a couple habits that die hard, and I'll tell you what those are. First of all, I will start, I know this is an expert audience, but I like to start from the very beginning, so I'm going to give a broad background. And the second is I will pause a few times for questions, because if I lose you at the beginning, I'd rather not have you be lost for the entire talk, but let's catch you up when I pause for questions. So today I'll talk about a machine learning way for measuring dynamical masses of galaxy clusters. This method reduces errors by about a factor of 2 compared to standard methods, and it does really well on the places where standard methods catastrophically fail. So now I've given away my punchline, and let's start from the beginning. So this is an image of the Coma cluster. Clusters are massive. I'm obligated to tell you that they're the most massive gravitationally bound objects in the universe. Every cluster paper and talk starts with that exact sentence. They contain hundreds, maybe even thousands of galaxies, all gravitationally bound. And Coma has historic significance because it is the place where Fritz Zwicky famously discovered dark matter. And this is the dark matter. This is the data from Zwicky's 1933 paper. He looked at these line-of-sight velocities and from them inferred that the objects in Coma are moving too fast to be gravitationally bound by the stuff he could count up and see. It turns out that the same things that drove Zwicky crazy in 1933 drive me crazy today. This question mark right here, he has no idea if that object actually belongs in Coma or if that's an interloper in the fore or background of the system. So, dark matter. He inferred the existence of dark matter from those line-of-sight velocities. And of course, one of the things that we like so much about dark matter is that it's pretty straightforward to model. So you start with a universe that is smooth with small density perturbations. And over time, the overdensities accrete more and more matter until you have this beautiful, beautiful cosmic web at late times, where you have filaments and voids. Do I have a laser pointer anywhere? I'll just point. Clusters are going to live in these most massive halos, and that's where you'll get your collection of galaxies. So Zwicky used, thank you. I think I just need the laser pointer, as a matter of fact.
Okay.
Yeah, just the pointer. There we go. All right, just in case. Zwicky used the Virial Theorem, which tells us how a cluster spends its energy as it's assembling. So it tells us how it spends its kinetic and gravitational potential energy as the matter is infalling. And just in very broad brushstrokes, I can write that kinetic energy as a sum of 1/2 mv squareds. The gravitational potential energy, I can look at pairs of objects, their masses and their relative distances. I think you'll believe me that I can massage this into a term about velocity, dispersion, total mass, and radius. And all of the details that I just massaged out, I'll dump in that alpha parameter and I'll constrain it with observation. And if I know the average density within those halos, I can even get rid of the radius term, and I can come to the conclusion that velocity dispersion should scale with mass as a power law. Now, we'll pin down these values exactly using simulation, but that is a sort of high-level, rough overview of what we're actually doing when we're looking at dynamical masses. We're going to look at the velocities, the velocity dispersion, and scale those with mass as a power law. So in simulations, what does this look like? What I'm showing here is log mass and log velocity dispersion of simulated clusters. I've got a nice power law with some significant scatter. And there are some physical reasons for that scatter. If you look down, if you have a very triaxial halo and you look down the long axis of that halo, you will tend to live up here. If you look down the short axis, you'll tend to live down here. Infalling matter and mergers, those will create a wide, flat velocity PDF, and these are actually really your troublemakers. The clusters that are undergoing mergers, recently have undergone mergers, or have a lot of infalling matter, those will live up along here. About 10% of clusters in simulations fall under that umbrella. And those get you into trouble because you can make an assumption about log normal scatter, but the merging objects, the ones that are accreting matter, are actually a long extended tail to that log normal scatter. And so assumptions about log normal scatter will break down.
This is 1 sigma and 2 sigma lines.
Those are 1 sigma and 2 sigma lines, yeah. And actually, this is a good time to pause for questions. Are there any questions so far? All right. Now, if I break up the clusters here, and instead of showing them mass and velocity dispersion, if I just collect the ones that live very much above the best fit line and the ones that live below the best fit line, let's take a look at what that looks like. So here I've normalized my line of sight velocity by velocity dispersion. So by design, all of these curves have the same dispersion. This solid gray is the full catalog. The solid blue are the ones that live far below the best fit line, the ones where you'll underestimate a mass. This dashed are the ones that live above the best fit line. We're overestimating their masses. And the dotted live well above the best fit line. We're getting their masses quite wrong. Now, what's interesting here is that the velocity PDF is giving you more information than we're using. In a dynamical mass estimate, we're using just the velocity dispersion. Here I'm showing you curves that all have the same velocity dispersion, and their shape is telling you how a dynamical mass estimate gets it wrong. One thing we could do is we could use the kurtosis, just a measure of how wide and flat those distributions are. So here I'm showing you kurtosis. These are the wide, flat distributions. These are the pointy distributions, kind of skinny and pointy. And here I'm showing you how far above or below the best fit line. So this is perfect estimate. These ones get overestimated. These ones get underestimated. So we can use the kurtosis as a way to correct a dynamical mass estimate. And I will tell you without showing it, that applying the kurtosis in this way can improve mass estimates by about 15%. You can gain about 15% just by using this extra information. Let me pause here for a second and tell you a bit about the cluster catalog that I'm using. So this is built with substructure in the multi-dark catalog. So multi-dark is a gigaparsec box. It's large enough that I have a good sample of clusters, but high resolution enough that I can resolve the substructure. So I'm going to pick up subhalos within the cluster. Up here I'm showing the most massive cluster in multi-dark. This is the edge of that cluster, really pale purple. These are this is the subhalos within this particular cluster. They're sized according to their mass, so the bigger ones are the more massive subhalos. They are colored according to their line of sight velocity. And along this top, these are 3 different line of sight views of the same cluster. So you can see that from any particular line of sight, you're getting very rich and very different information.
Can you say one more word about?
Yeah.
You're making these. I know it says ideal at the top.
Yeah.
These are so ideal; they're all perfectly round.
Yes. So right. So I'm going to show you a less ideal catalog in just a minute. That's my next slide. That I like these questions because it means I'm telling a good story. It means you're wondering about what's going to happen next. So in the ideal catalog, I know exactly what belongs in the cluster. I'm using a spherical overdensity halo finder, or multi-dark rather, uses a spherical overdensity halo finder. So they are perfectly round, but you can start to pick up on some of the triaxiality in this, a more typically sized cluster, and you get different information depending on which line of sight you're looking. All right? So I hope that a room full of people who love data are a little bit horrified that the standard method is to take this rich data set and summarize it as a velocity dispersion, full stop, and that's the only information that we're going to use about it. So what I want to present now is a way to pull more information and utilize more information. So this is my ideal cluster catalog. You ruined my punchline for this, but I'll also use an impure cluster catalog where I do something very simple. I have a set aperture, a set line of sight velocity cut. I'll cut a cylinder around every cluster. I will get a ton of interlopers. It'll be a messy, ugly catalog, but I will do the exact same thing to every single cluster, and we'll see what shuffles out. Okay. The next thing I want to do is I want to introduce the machine learning tool. So let me pause here. Are there any questions about clusters for cosmology, the catalog that I'm using?
When
Yes.
you do this, are you doing this on the big clusters that you do, or are you doing this on the subclusters within them when you make this catalog?
Yeah, so when I make this catalog, this is centered on a 10 to the 14 M solar per H cluster or larger.
Okay.
And I'm picking up all of the primary and subhalos according to the multi-dark definition within that very large aperture and velocity cut. Other questions? Yeah.
Are you very sensitive to the central again?
So that's a good question. So for this, I am assuming that the center of the cluster is known. Yeah, but that's a very good question. So I have done some other work using cluster dynamics and forward modeling of cluster dynamics. And if one does the same thing with the simulations and observations as far as determining the center, I think you should be fine. Yeah. So I have looked at sort of iterative recentering schemes. The punchline here is going to be that it's not going to matter so much as long as you're consistent between your sims and observations. But everything I'm showing here is just sims. All right. So the tool. Let's talk about how we can reduce mass error with machine learning using the support distribution machines regressor. So I want to start with a really technical and math-heavy introduction to machine learning. I'll give you a second there. All right, I like this one. I think Randall Monroe, this is for an XKCD cartoon, if you all don't recognize that, sort of right off the bat. I think Randall Monroe gets it really right here. The machine learning tool that I'm using really is a big old pile of linear algebra. This part right here, stir the pile until they start looking right. I think this points out something, a nuance about machine learning tools, and that is this. It's as much an art as it is a science. The tool that I'm using wants to reduce root mean squared error. I, as a cosmologist, want to get the really rare clusters right. And so there's a bit of an art in taking the metric that the tool is using and the metric that I am using and getting them to talk to each other. All right? We're not going to stir the pile until the answers look right, but we are going to carefully build a training catalog that communicates to the machine learning tool that the massive clusters are just as important as the low mass clusters. Okay, so no math. I promised you math heavy, but that was it. The support distribution machines regressor is the tool that I will use. From a distribution, it predicts a scalar. What I mean by that is from a distribution of galaxy properties, line of sight velocity, plane of sky position, anything that you think you can simulate the distribution of, well, it predicts a scalar. The log mass is what I'm after. And to help you understand what the support distribution machines regressor does, I want to start with a base case, which is a support vector machines classifier. So for support vector machines classifier, this is supervised learning, meaning that I have labels attached to my objects, so my training objects. So here I've got some data vector, input X and input Y, and I've marked the end of the data of that vector with either a triangle or a circle. And those are my labels. So from some input X and input Y, my training data is all labeled. I want to decide if this is going to be a red circle or a blue triangle. And what I'll do here is I'm going to move into a higher dimensional space such that I can separate my two classes by a hyperplane. And then that hyperplane becomes the decision boundary. So now if I have some unknown data vector and I move it into this space, if it's above my black plane, I'm going to say that must be a red circle. And if it's below the plane, it must be a blue triangle. Okay, so this is the base case. This is one of the standard tools that is available on something like scikit-learn. But the support distribution machines is now going to go a little bit farther in two key ways. First, we're going to regress, not classify. So I'm allowing a continuous valued label. Okay, that's pretty easy to imagine. And the second is the input is a distribution, not a data vector. I'm going to unpack that in my next slide, but I just gave you a lot of information. And so I'm going to pause again here and see if there are any questions before I unpack point number 2. All right. So when I have an input that is a distribution, not a data vector, the tool that I'm going to use here is the KL divergence, which is just going to give me a measure of how similar or different two distributions are. So here I'm showing PDF P of X, that's the red line, and Q is the blue dotted. And if I want to measure the KL divergence, what I'll do is I'll integrate over all X, P times log P over Q. And you can integrate this by I. And what I'm going to do is I'm going to slide Q over a little bit, and exactly what you think should happen does happen, which is as they get farther and farther apart, that integral gets larger and larger. Similarly, if I keep my P the same, but I'm just going to now keep them centered at the same place and squash Q down, as Q gets more and more squashed, the integral gets larger and larger. So this is going to be our way for quantifying how similar or different two distributions of data are.
What does KL stand for?
Where does...
KL.
It's the KL divergence is two names that I cannot pronounce. Kullbach is the first one, and the second one I'm not even gonna make an attempt at. Yeah. Okay, so to motivate the idea that this might be a useful way of describing cluster dynamics, what I want to show here is binned up by mass. These are my low mass clusters coming across, and then across the bottom, these are my highest mass clusters. I've just dumped them all into the same PDF. What I'm showing here is line of sight velocity and line of sight velocity divided by velocity dispersion, so that I have a nice pretty 2D distribution to show you. And I think you believe that if I pulled 100 or 200 or 300 objects from one of these distributions, and I gave you those 200 fair draws, you would be able to make a pretty educated guess as to which of these distributions those fair draws came from. And that is kind of the meat of what this machine learning tool is doing. It's taking some distribution from a cluster of unknown mass. It's comparing them to distributions of clusters of known masses, and then from that, predicting the cluster's mass. Here are some results. What I'm showing here is error, fractional error. Of course, I would love nothing more than a spike right at 0. I'm giving you a PDF here. This red solid line is my ideal catalog with the standard power law method. So in this case, I know exactly what belongs in the cluster, and I use my M sigma power law relation to predict a mass. And I get this extended high error tail that I'm not super pleased about. These are the ones where I'm really overestimating cluster masses. Those are going to get me into trouble when it comes to cosmological constraints. All right? Using that same catalog, the ideal catalog and support distribution machines, gives me this blue PDF right here. So not only have I reduced errors by a factor of 2, but I have also nearly eliminated those high error objects. Okay, but that's an overly ideal case. So what about the case where I cut a cylinder around my clusters and I don't know exactly what belongs in them? A more reasonable and observationally feasible catalog. When I cut those cylinders, I get, and I use the standard power law method, I get this right here. Okay, this extends kind of out into the parking lot, not shown, but it goes pretty far. The catalog that produced this orange dashed mess here, when I use the machine learning tool, I get this green distribution right here. So interestingly, I'm even reducing errors compared to, let's see, the red ideal power law case. So if you look at the red, this is the ideal catalog power law, the standard method, when I know exactly what belongs in the cluster. And the green is the machine learning, when I've just naively cut cylinders around each cluster. Okay. If you're maybe a little bit suspicious, you would like to know, yes, but maybe that's just for the average catalog. Maybe you're just guessing the average mass the whole time, and what you're showing is weighted by the low mass objects. Let me put your mind at ease here. Here's what I'm showing is the middle 68% of errors as a function of mass. All right, so the white is, I've predicted mass perfectly. The red is the pure catalog with the power law. It spans from here to here. The blue is the impure catalog with the power law. And using the data that created the blue with the machine learning tool gives me purple, which does well at all mass ranges. So it's not just that I'm doing well at the abundant low mass clusters. Questions here? Yeah.
So why bias low?
Yeah, why bias low? So let's see. I am not sure that I have a plot here. Machine learning does very well with interpolating and not so well with extrapolating. So near the edges, let's see, I don't have a chalkboard or anything. Okay, I'm just going to have to gesture wildly. So near the edges of here's a 1-to-1 line. Near the edges, the predictions are going to tend to pull down toward the mean and up down there, and like up toward the mean up here. The reason why that happens at the high mass end, the reason why that happens is at the very high mass end in my sort of small mass bins, I only have 5 or 2 clusters. And I've done everything that I can to squeeze as much out of that data as possible. But when I only have a handful of clusters in a bin, I can't really tease out exactly what clusters in that mass bin tend to look like. Because we're touching on it now, let me also describe a little bit about what I've done to squeeze as much out of the data as possible. So I said earlier that there's a little bit of an art to machine learning. And this tool wants to reduce root mean squared error, which means if I give it a halo catalog, it's going to get the abundant low mass clusters right. And it's going to say, I don't need to get the high mass clusters wrong because there's only 5 of them. So why does it matter? It doesn't really affect that root mean squared error. So for this project, I created a halo catalog with a flat mass function. I did a lot of rotations at the high mass end, subsampled at the low mass end, which is a really good way to communicate that every mass is important. But going back to your original question and just trying to answer it very concisely, the reason you tend to have this little bit of bias is the pull toward the mean. Yeah. Other questions?
Which of those lines represents the best place you can do observation with real?
Not shown, but I think that the best that one could do observationally is somewhere between the blue solid and the green dashed, right? This is an absolutely ideal catalog. This is a very naive cylinder. Using a smarter method like a caustic method for identifying cluster members would put you somewhere in between there. Yeah. Other questions? All right. So I want to conclude with some big ideas, and then I'll take more questions if anybody has any questions. So the Virial Theorem, we motivated this by the Virial Theorem. The Virial Theorem motivated M sigma power law has broad scatter and extended high error tails. Over and under predicted halos can sometimes be identified by their kurtosis, and you can use that to correct for sigma. Machine learning can be used to take full advantage of the velocity PDF, and this tool support distribution machines can decrease error by about a factor of 2 compared to a standard method, even when you use clusters that have been contaminated by interlopers. Thank you.
So, your point too about
Kurtosis
being useful.
Mhm.
Did you go in with that idea, or did you find the idea, that from looking at your data?
Yeah, so these things get peeled off in layers, don't they? So the plot that I showed toward the beginning, where I showed the different ones with the kurtosis, is something that I found playing around with the data. But upon peeling further, realized that Gus Everard found it before I did. But I think I was the first person to use it as a correction term. Yeah, so this idea of clusters that are undergoing mergers having a wide flat velocity PDF is not a new one. But using that subtle signal and using that subtle signal to motivate a machine learning approach is, yeah.
So you're trying to connect this velocity distribution to the cluster mass. The Virial Theorem says it's more related to things like gravitational potential, which can in principle also be predicted from theory.
Mm-hmm.
So will you gain more without doing machine learning, but simply using time, the measurements to a better theoretical variable?
Can you expand that question a little bit more?
Well, you're trying to mass. Mass is not directly related to velocity, but gravitational potential is. So you have models for the mass functions in different cosmologies. So this is what you're trying to do, right? You want to approximate cluster masses by observations. But you could also predict gravitational potential distribution for the cluster population in different cosmologies. And by Virial Theorem, your velocity dispersion is more directly tied to gravitational potential. So you immediately can expect a lot less scatter between the gravitational potential and velocities.
So I love this question.
I'm just thinking by being smart, you can gain more than by going this techniques.
So a clever reader will notice that these papers are a little bit on the older side. And what I've been working on lately is actually a forward modeling approach that takes cluster dynamic measurements and goes straight from the cluster dynamics to the cosmological constraints. And I think that at the heart of what you're saying is, could something like that be done? And I'm going to say yes, and watch the archive, because you may see it done in the next something like 2 weeks. Yeah, okay, all right, good.